Okay, this is chapter 6.4, transformations of exponential and logarithmic functions. So now we know what an exponential function looks like and a logarithmic function. Now we're going to move them around. The essential question, how can you transform the graphs of exponential and logarithmic functions? And what you will learn is how to transform graphs of exponential functions, how to transform graphs of logarithmic functions, and how to write transformations of graphs of exponential and logarithmic functions. So let's have a look. Okay, so let's talk about this concept of transforming graphs of exponential functions. So you can transform graphs of exponential and logarithmic functions in the same way you transform graphs of functions in previous chapters: parabolas, radical functions. Examples of transformations of the graph of f of x equals 4 to the x are shown below. So we have a base 4 in an exponential function. Okay, so if we're going to shift it left or right, it's f of x minus h. So notice that is going to end up in the exponent. So a left-right shift is going to be a plus or minus in the exponent. So 4 to the x minus 3 as a power, 4 to the x plus 2 as a power, we'll move it left and right. And it's still opposite directions of the sign as it were before. Vertical translations is when you take a constant and add it or subtract it to the end, f of x plus k. So now we have our 4 to the x parent function right here. F of x is 4 to the x. And if you add a constant after it or subtract a constant after it, that moves it up or down respectively. Okay, reflection. The graph flips over x or y. If you want to reflect it in the y-axis, you make the exponent negative. If you want to reflect it in the x-axis, you make the base negative. Okay, horizontal stretch or shrink. The graph stretches away from or shrinks towards the y-axis. It's f of a times x. So if a is greater than 1, it's a shrink by a factor of its reciprocal. If it is a fraction, it's a stretch by a factor of its reciprocal. That's horizontal. Remember, you have to do the reciprocal for horizontal. Vertical stretches or shrinks would multiply the base by a constant greater than 1 is a stretch, and multiplying it by a fraction between 0 and 1 would be a shrink. Okay, so that's the transformations of exponential functions. Okay, so now we're going to translate an exponential function. Example 1 says, describe the transformation of f of x equals 1/2 to the power of x, represented by g of x equals 1/2 to the power of x minus 4. Okay, so what we're going to do here is, first of all, what kind of translation is that? So the parent function is right here. This is the parent, if you will, base 1/2 to the power of x, and it's getting translated. Well, it is being translated by a constant k minus 4. This will be a shift down 4. Okay, so now I'm going to graph this, and let's see, I'll graph the original parent function f in blue. So let's change this color to blue. I'll just leave it there. And here we go. I'm not going to make a table of values. This is really easy to do with integers. 1/2 to the power of 0 is 1, because anything to the 0 is 1. So when x is 0, the function's value is 1. So the parent function is going through the point 0, 1. If I plugged in a 1, it's 1/2 to the first power. That is a half. So if I go over to 1, I am at a 1/2 point. If I plug in 2, I'm down to a quarter. If I plug in 3, I'm down to an 1/8. Okay, and it just keeps getting lower and lower. If I plug in 4, I'm down to a 1/16. And it's getting closer and closer and closer to the x-axis. Now, if I plug in a -1, that's going to be 2. It's the reciprocal of the base. If I plug in a -2, it's going to be 4. Okay, so those are the points, and I'm not going to try to draw that because I'm just going to make it a mess. I'll leave the dots for now, and then I'll bring in a graph that's printed by Desmos. All right, so this is going to be shifted down 4. So the first thing I'm going to do is just shift every point down 4, and then I'll check my value. So this is at 4, down 4 is at the point -2, 0. 1, 2, 3, 4 would be here. 1, 2, 3, 4 would be here. And then this is 1/2, so that'd be -3.5. This is a quarter, so that'd be -3.25, which would be right here. And then this one should be here, and then this one should be about here. So there it is, shifted down. And so now I'm going to check the values though. So if I plug in a -2, 1/2 to the -2 is 4. 4 minus 4 is in fact 0. If I plug in a -1, it is 1/2 to the -1, or 2. 2 minus 4 is -2, and that is the point I plotted. If I plug in a 0, 1/2 to the 0 is 1. 1 minus 4 is 3. -3. 1 minus 4 is -3, so it's 0, -3. So my values do seem to appear to be correct. All right, so there it is graphed, and I will bring in the parent function from Desmos now. Okay, so here is the graph from Desmos, nice smooth curves going through the same points that I have plotted over here. Okay, so there is the parent function f of x equals 1/2 to the x, and this is a shift down, putting -4 after. Now you should be able to do problem number 7 and 8 in your problem set. Okay, here we go again. Translating a natural base exponent function. Describe the transformation of f of x equals base e to the x. So that's the natural log. Okay, or the natural base, I should say. The inverse is the log. It's base e. Remember Euler's number, represented by g of x equals e to the x plus 3 plus 2. All right, so the parent function is going to be, let's do it in blue, I guess, e to the x. So I'll do this in blue. And the transformation function in red. Okay, so before I even talk about this, well, actually, no, it says describe the transformation. So the +3 in the exponent means shift left 3. So it's going to be a shift left 3, comma, and the +2 is a shift up 2. So shift up 2. Okay, so I'm going to plot the parent function base e to the 0. E to the 0 is 1. I'm going to put a dot right there. And this one is a little more difficult to choose values because we have to know what the value of e is. So I'm going to use my calculator for this time. So I'm going to hit clear, and e is 2.718. So if I plugged in 1, that'd be e to the 1, or just simply e. So over 1 up 2.7, a little bit more than 2 3/4. Here's a half. So I'd say about right here. Okay. Let me get my calculator back. Actually, let me just do this. Okay, so now I'm going to do e squared and hit enter. And that's going to be 7.389. So if I go over to 2, that's going to be 7.3. So 7.5 is here. So I'd say maybe right about here. So this is coming down. And then when we go to -infinity, it's getting closer and closer to 0. So if I plugged in a -1, that would be e to the -1. That would give me 0.367, about a third. -1, 1/2 is here, so I'd say about here. Okay, and then if I plug in e to the -2, that's going to give me a value of 0.135, -2.135, 1/10. So about here maybe, and it's going down closer and closer to 0, but we'll never get there. So there's the graph of e to the x. Now we're going to translate that 3 units left and up 2. I'm not going to use the calculator to do this. Let me maximize this back up. So if this point here is going to get shifted left 3, that's 1, 2, 3. And then up 1, 2 would be up here somewhere. I'm off the grid. Do the same here. 1, 2, 3. Up 1, 2 should be right about here. 1, 2, 3. 1, 2 is right here. 1, 2, 3. 1, 2. And then 1, 2, 3. 1, 2. So this is going to have an asymptote at y equals 2. Okay, so our constant in this case is going to be our horizontal asymptote, and that's going to grow to infinity. So now let me bring in the graphs so you can see them without just the points. Okay, so the graph on the right here is what I plotted by putting values in. Here's what it would look like if you graphed it using a technology device such as Desmos. And there is the horizontal asymptote at 2, telling us that this red function, which is shifted left 3 up 2, will not cross that asymptote. Okay, so now you should be able to do problem number 10 in your exercises. Okay, example 3a, transforming exponential functions. So this says describe the transformation of f represented by g, then graph it. So it's an exponential function with a base 3. Okay, so that is going to be our parent function, f of x. So we're going to plot this first. 3 to the 0 is 1. 3 to the 1 is 3. 3 squared is 9. So way up is getting big really fast. 3 to the negative 1 is a third right here. 3 to the negative 2 is a ninth, and so on and so on. So there's the graph of f of x. G of x, now notice what's going on here. Let me see. A equals 3, and h equals negative 5, or h equals 5. So that means we have this. So notice that the function is of the form g of x equals 3 times ax minus h, where a is 3 and h is 5. So 3, what does that mean? Well, the 3 being an, let's see. All right, so the a being a 3 is going to be a horizontal shrink. Remember, vertical stretches and shrinks are when a is out in front being multiplied. When a is in the exponent and it's your coefficient of your variable, then it is a shrink. So that is a shrink of 1/3. You take the reciprocal when it's horizontal shrink of a third, and the minus 5 is going to be shifted right 5, because it's opposite when it's in the exponent. Okay, so it's going to be shifted right 5 and shrunk. Okay, so let's take a look. Okay, so I'm going to use my calculator to do this. So I'm going to plug in values. So it is 3 to the power of 3 times 0 minus 5, which would be 0. So let me just do that. Clear. 3 to the 0 minus 5 is 3 to the negative 5. And that would be really close to 0. So let's do that in red. So negative 5. When I plugged in, what did I plug in here? 3 to the 0. So at 0, and x is 0, y is 0.004. Really, really close to 0 right here. What's this doing? Right here. Okay. If I plugged in a 1, that'd be 3 to the 3 minus 2, or 3 to the negative 2, which is 1/9. So it's still not very high at 1. It's right here. And then finally, if I plug in a 2, that'd be 3 to the 6 minus 5, which is 3 to the 1, or 3. So now I'm right here. And then if I plug in a 3, 3 to the 9 minus 5 is 3 to the 4th power. Then it's really big. Then it gets big really fast. 3 to the 4th is 3 times 3 is 9 times 3 is 27 times 3 is 81. So that would be 3 comma 81 and way up, but this only goes to 8. So I'm going to go the other way, and it's getting closer and closer to 0. And so this is what the two graphs would look like. Okay, so now that I've done that, I'm going to show it to you from the Desmos point of view with the graph drawn through the points. Okay, so this is the graph over here. This is what it looked like in Desmos. So there is the okay, so there's the shift and the shrink. Okay, right there. The blue one is the f of x is 3 to the x, and the red one is g of x is 3 to the 3x minus 5. So now you should be able to do problem number 19 in the exercises. Okay, example 3, another transformation. Describe the transformation of f represented by g. This is example 3b. Then graph each function. So f of x is e to the negative x. Okay, so e to the negative x, and then g of x is negative 1/8 e to the negative x. So for starters, our parent, or not our parent function, but our beginning function, our first initial function is a reflection of the parent function. And let's go back. Remember what the rules say. So if you have a negative in the exponent right here, f of negative x, it is in the y-axis. So a negative exponent x will be a reflection in the y-axis. Okay, so let's now go back to the problem we're on. So think of e to the x, it's a reflection in the y-axis, so it's going to flip over the y-axis. So instead of going up like this, so I'm going to draw that up really quick. So e to the 0 is 1. So e looks like this, if you will. So if you reflect it in the y-axis, it's going to go like this. Okay, so let's take a look. So that's that one. And then we're going to take the initial function and then this negative 1/8. Well, what's that doing to the function? So the next thing we're going to do is it says, notice that the graph of the function is in the form of g of x equals a times e to the negative x, where a is negative 1/8. So the graph of g is a reflection in the x-axis and a vertical shrink by a factor of 1/8 of the graph of f. Okay, so we're going to, this is a reflection of e to the x in the y-axis, and then g of x is going to reflect it across the x-axis and shrink it by a factor of 1/8 vertically. Okay, so let's take a look at what that will do to the function. So the parent function I'm going to do, or not the parent, but the initial f of x is going to be done in blue. So e to the negative, if that's 0, e to the 0 is 1. E to the 1, negative 1. So I'm going to use my calculator here. So we'll open the calculator up and shrink this down and turn it on, clear, and take second, clear, second e to the power of, let's put a 1 in. So when x is 1, that'd be a negative 1. And that's 0.367. So that'd be the 0.367, about a third. So it'd be about right here. Okay, and then we're going to do second e to the power of negative 2. So when x is 2, that's going to be 0.135. So this is coming down like so, and it's probably going to get closer and closer to 0 like that. So I'm going to go the other way now. To get a negative 1 in this function, it's got to be, x has to be negative, or has to be 1. So now I'm going to do e to the negative 1, which is e to the 1. So second e to the 1 is just e, or 2.718. So negative 1, 2.7 is about here. And then finally e squared, second e squared is when you plug in a negative 2, because the negative 2 is positive 2. We're going to get e squared at negative 2, and that's 7.3. So then it's way up here. And it comes down real quickly like so. And now we're going to graph this one. So this is going to be a reflection in the x-axis and a shrink. by a factor of an eighth. So let's just plug the values in. So when I'm going to put the function in as negative 1 divided by 8, negative 1/8 e to the power of 0. We'll start at the origin. I get negative 1.125. Okay, so negative 0.125 is about here. Okay, and then I'm going to plug in a -1 and so on. So I'm just going to hit second enter to bring back my function. And all I'm changing now is this x at the end right here. So in order for that to be a positive 1, I have to put a -1 in, and that would make that to the first power. So that's with a -1 substituted in. At -1, I'm at negative 0.339 or negative 0.4. So about a third, a little more, so right about here. So then I hit second enter to bring that back. I'm going to switch that e to the 1. Now if I plugged in a -2, that'd give me a +2 here. And that is negative 0.9, so almost -1, so right here. So this is turning and going this way. And we're getting closer and closer to 0 this way. I don't need to use my calculator anymore. It's going to have the same horizontal asymptote at the x or y equals 0 or the x-axis. Okay, so there are the two graphs. So those are just the dots. So I will plot this in Desmos and bring that graph in. Okay, so here is the graph in Desmos. I've got the dots over here. Here's what it would look like if you connected those dots. Nice smooth curves, horizontal asymptote at y equals 0. Okay, so now you should be able to do problem numbers 18 in the exercises. Okay, transforming graphs of logarithmic functions. Examples of transformations of the graphs of f of x equals the log of x are shown below. Okay, so if we have a minus h, x minus h in the parentheses, it'd be g of x equals the log of x minus 4 as an example. That'd be 4 units right. X plus 7 in parentheses would be 7 units left. So the rules are the same. The log of something in parentheses, you move opposite directions. A vertical transformation is when it's log of x with a constant after, not in parentheses. So log of x plus 3 is 3 units up. Log of x minus 1 is 1 unit down. If you take the log of a negative, it's a reflection in the y-axis. And if you negate the log of x, it's a reflection in the x-axis. Horizontal stretches and shrinks are when the numbers inside the parentheses, a number greater than 1 is a shrink by its reciprocal. A number between 0 and 1 fraction is a stretch by a factor of its reciprocal. And vertical stretches and shrinks are numbers in front. So 5 times the log of x is a stretch of 5. And 2/3, a number between 0 and 1 times log of x is going to be a shrink by that factor. Okay, so it's the same rules. You just have to know where these changes appear in the new functions. So let's take a look at that. Okay, so here's example 4, transforming logarithmic functions. Okay, so we've done exponentials. Now let's do the logarithms. Describe the transformation of f represented by g, then graph each function. So the first thing we're going to do is look at this. So here is the parent function, or not the parent. No, that is the parent function, actually, log of x. Okay, there's the parent log x function. Let's take a look at that. So if I just take the log of 0, I get an error. Okay, so I cannot take the log of 0. That has to be greater than 0. So I'm going to clear, and I'm going to take the log of 1. So I now know that there's a vertical asymptote at 0. So now I'm going to take the log of 1. So these are all the things you need to think of while you are doing this. So the log of 1 is 0. So if I go over 1, I'm at the y value 0. So it's right here. If I go to log of 2, I get 0.3. So go to over to 2, I'm up a third, which is about here. And now I'm going to take the log of 3, and that is 0.47, almost a half. Log of 3, close to a half. And log of 4, is 0.6. So it's a little more than a half. So as you can see, this is growing slowly. And log of 5 is almost 0.7. So almost 3/4. And what's the log of 10? I'm going to skip now. Log of 10 is 1. So if I go up to the log of 10, that is 1, which means 10 to the 0 is 1. The log base 10, so it's 10 to the 1 equals 10, I mean. Remember, log, the base here is 10. That's a common log. And so that means the log base 10. And if I take the log base 10 of 10, we have that rule where they cancel and they just become 1, or 10 to the first power equals 10. Okay, remembering that from the last chapter section. So we finally came up and got to 1. Okay, so this point right here looks like it's not growing fast enough. So this should be a little bit higher, probably like right about there. So what's going on between 0 and 1 though? So now I'm going to take the log of 1/2. And the log of 1/2 is negative 0.3. So the log of 1/2, here's 1/2, negative 0.3, almost a negative third right there. And if I take the log of 0.1, 1/10, that's negative 1. So the log of 1/10 is negative 1, which is right here. So this is getting closer and closer to here. Remember, we can't take the log of 0. So there is the function graphed. Now, what does the log of negative 1/2 x do? Okay, so remember the rule. The coefficient of the variable is being taken within the log function. So if I go back, what we have here is this. So that's a reflection in the y-axis, but it's also a fraction. So it's going to be a stretch by the reciprocal. So this is a reflection in the axis plus it's going to be, let's go back. 1/2 would be a stretch of 2, stretched by a factor of 2 reflected in the y-axis. Okay, so we're going to reflect this in the y-axis. So this is going to come this way, but it's going to be a stretch by a factor of 2. Okay, so that's a horizontal stretch, yes? Horizontal stretch, so it's going to grow slower. All right, so let's plug some values in. I want to take the log of negative, I'm going to use 0.5 just to be easier to type in rather than 1 divide 2. 0.5 is a half. Negative 1/2 times 0. Guess what's going to happen there? Error. I can't take the log of 0. So I'm going to do the log of negative 0.5 times 1. And that's going to give me an error, non-real answer. So there's no values over here on this side. So we now know that the vertical asymptote is the y-axis, but we're going the other way. So now I'm going to take the log of negative 0.5, and I can't plug in 0. I have to go negative. So it's going to be times negative 1, which will give me negative 0.301. So that will be, I plugged in negative 1. And that's going to be negative 0.3, negative a third, which is about here. So if I redo that, I'm just going to hit second enter and change that last number. So now if I make that 2, that's going to be 0. So that's right here. And second enter, bring it back and go to negative 3. And that's going to be 0.176. So right about here. And bring it back. And that's 0.4. Not 0.4, I meant 4. Second enter. I don't want a decimal yet. Delete that decimal. At negative 4, it's 0.3, a third. So it's getting bigger. And now let's go out to times negative 10. Second enter. And let's make this a 10. So that's actually going to be 5. So that's 0.69. So at negative 10, it's going to be a little bit more than a half right here. So that's what that's doing. And it's coming down. And I'll do one more. I'll plug in a half. So I'll hit second, enter, and I'll make this negative 0.5. And that's going to give me negative 0.6. So at a half, it's a little bit more than a half. And now that's coming down like so. So now I'll pause the video and I'll bring in the graph from Desmos, and it should look like this, but with solid lines. Okay, so here it is graphed. And so these were the dots that I plotted using the calculator, and this is what it looked like from Desmos. Okay, so now you should be able to do problem number 27 in the exercises. Okay, example 4, we're going to do part B in this page. It says to describe, same thing, transformations represented by G, then graph each function. So we have the log base 1/2 of X, and then we're going to put a 2 in front. So that's one thing that's defining our transformation, and a +4 inside. So what does that mean from our rules? Well, it's in the form of a times log base 1/2 of X minus H. A is 2 and H is -4. So A is 2, H is -4. What does that do to the function? Well, the graph of G is a horizontal translation 4 units to the left and a vertical stretch by a factor of 2 because the number's out front, not in the parentheses. Okay, so that's what we're doing. So let's take a look. So let's graph this. So I'm going to zip this down like so, and I'll plot points on this. So turn the calculator on, clear the last problem. I'm going to do log base 1/2 of X. So I'm going to put log. And in plugging these into the calculator, there's a trick to this. I'm not going to explain it in much detail, but you take the log of the number you're putting here and divide it by the log of 1/2 to get the value. And I'm not going to explain that at this moment. It's in for future chapters, but I can't take the log of 0, can I? Log of 0, if I hit enter, it's going to be an error, right? So I can't do that. So I'm going to take the log of 1. I'm going to start with 1. And I'm going to divide that by the log of 1/2, which is 0.5. So that would be log base 1/2 of 1. That's how you enter that in the calculator. And I get 0. So at X equals 1, we're at 0. Okay, so that is right here. And now I'm going to say second enter. The only thing I am changing, by the way, is this number right here. This is the log of 1/2. Our base does not change. The X I'm actually plugging in is the first parentheses. So I'm going to change that to a 2, and that will give me -1, which is right here. Okay, so 2, -1. All right, so now I'm going to plug in, I'm going to bring that up, and I'm going to go back over to here and try 3. And that's going to be -1.58. So 3 is -1.5 and a little more. So I'd say right about here. So as you can see, this thing is starting to turn and go this way. I'll do one more, second, enter, bring that back and go back to 3 and make it a 4. And that is going to be -2. Log of, so the log base 1/2 of 4 is -2. Okay, so there it is. And as we're getting closer and closer to 0, that should grow faster. And we can't get to 0 because there's a vertical asymptote. So I'm going to hit second enter and just get a value in between. We did 1. Now let's do 0.5, which is a half. And that is going to give us an error. So I can't even, that shouldn't be an error. Let me go back. Maybe I entered it wrong. Oh, I didn't close the parentheses. Okay. All right, I see what happened. Second enter. I need to insert a parentheses here. Putting the negative gave me, or decimal gave me one more position, and it was dividing in the wrong place. So there we go. Log of -1/2 is 1. So when X, I'm sorry, log of 1/2. So what I did was log base 1/2 of 1/2 is 1. Okay, remember that rule, it cancels. Log base, if the base is the same as what you're taking the log of, the answer is 1. And so as you can see, this is getting bigger, faster, and I don't need to go any further. So now I'm going to move this 4 units left and then stretch it. So I know all these points are going to be over here and then stretch. So this should be curving somewhere over here. All right, so I'll change to red. And now I'm going to do 2 times the log of 1/2. So I'm going to put a parentheses here. I'm going to put a 2 out in front. And now it's going to be X plus 4 And let's start with 1. So 1 plus 4, 2 times 1. So x is 1. 1 plus 4 divided by, I need another parentheses here. Second, insert a second parenthesis. So I'm multiplying 2 times this whole thing. That's what the 2 out front is. So the log of x, which is 1 plus 4, divided by our log of our base. So that's going to be the log of our base, which is a half. And hit enter. And I got negative 33 when x was 1. That's not right. So how am I supposed to enter this in the calculator so I get the correct answer? So it's 2 times the log of 1/2 x plus 4. 2 log 1 plus 4 is 5. Well, maybe that was right. Okay. Anyhow, I don't want to take the time to do this. I've done plenty of these. You're probably losing interest. So let me just put this in Desmos because it's tough to do with the TI calculator. I can do it in Desmos a lot easier. So let's show that in Desmos. So I want 2 log 1/2 x plus 4. So let me bring Desmos over here. Here it is. And I want 2 log base 1/2 x plus 4. I'm going to call it g of x equals 2 log parentheses. Actually, I want a base here. So let me delete that. And let me go to functions. Here it is. 2 log 1 divided by 2. Whoops. Try that again. Function. I want the log base. Okay, so if I come down here, where is it? Number theory? No. I just saw it a moment ago. There it is. Calculus. So 2 log, and I want a parentheses here. No, it's not letting me do that. How about I just put 0.5? Okay, it's the only way I can enter that, I think. So 2 log 0.5 is my base, and I want x plus 4. Okay, there it is. And my original was f of x. And it was, let's see, log base 1/2 of x. So where's my Desmos? So function, calculus, log base 0.5 x. Okay, so there's what I had graphed on the in my graph with the dots. Here is it. Here it is shifted left 4 and a stretch of 2. Okay, so that's what the graph should look like. So with that being done, you should now be able to do problem number 28. Okay, and plugging this into a Texas Instruments calculator is actually pretty difficult. So I'll have to look into that for when we get to that in that chapter. All right, writing transformations of graphs of functions. So now we're going to write transformations of exponential functions. Let the graph of g be a reflection in the x-axis. So that's the first thing. It is a reflection in the x-axis. I brought the rules in, and those came from page 318 in the text. So if you're following along in the text, it's page 318. And I'm just going to refer to that while doing this until I memorize it, because these are new to us in this chapter section. You need to memorize these and be able to use them. So a reflection in the x-axis, it's a reflection in the x-axis is right here. and that puts a negative out in front, okay? Followed by a translation 4 units right. That's a horizontal translation. Units right are in the exponent. And here's the graph f of x. So what I'm going to do is take my pen and I'm going to write f of x equals 2 to the power of x. They want us to write a rule for g. So that's g of x equals. So I'm going to have a 2 as my base. That doesn't change. And I want 4 units right. So that's going to be x minus 4 in the exponent. And a reflection in the x-axis puts a negative out in front. So there it is. So g of x equals negative 2 to the power of x minus 4. So let me just make this look a little better here by, bringing all this closer. There we go. G of x equals negative 2 to the power of x minus 4. Okay, so there's example 5. So now you should be able to do problem numbers 35 and 36 in the exercises. Okay, so I'm going to get my highlighter here, write a transformed logarithmic function. Let the graph of g be a translation 2 units up. That is a vertical translation up 2. So that's what it's going to do. The function is a constant at the end. We need to be careful here because when you take a multiple of the outside, it's got to be distributed. So then it's a vertical stretch by a factor of 2. Vertical stretch by a factor of 2. So I'm going to name that g of x. So f of x, the original function, equals the log base 1/3 of x. Okay, so the way I want to do this, so I want to be careful. I'm going to call g of x. There's 2 changes. So let's call the first change h of x. So h of x is going to equal the original function f of x. And we're going to do the vertical translation first. So in order to do the vertical translation, okay, vertical translation 2 units up, we're going to take the function f of x and add 2 to it. Let me change colors there. So I'll use blue or green. How about green? F of x plus 2. So this is just the first step, 2 units up. Okay, so it's f of x plus 2. Then I substitute in my f of x, which was log base 1/3 of x, and now it's plus 2. Okay, and then the second step is we want to come up with g of x. So g of x is going to equal the stretch by a factor of 5, puts the number in front, multiplied. We have a stretch by a factor of 2. So g of x is going to be 2 times my h of x. Think of it that way. So it's 2 times h of x. So g of x is going to equal 2 times the log base 1/3 of x plus 2. Okay, and so now I'm going to distribute that. So 2 times the log of 1/3 x is going to equal 2 times log base 1/3 of x. And I need to distribute it to the 2, and 2 times 2 is 4. So be really careful with these. Always do the first step first, and then come back and do the second step. So that's how you do a transformation of a log function. So now you should be able to do problem numbers 39 and 40 in your exercises. Okay, this brings us to the end of chapter 6.4. Please do these problems, and thanks for watching and have a great day.